Hello! Today we're going to solve a word problem. I'm not even going to tell you what kind of word problem it is, but I'm going to read the problem for you. I only have one whiteboard, so writing it out and then reading it and then erasing it might take up too much of your time. However, I am going to write out the problem in the comments so you'll be able to follow along. So, this is about a 10-foot plank. A 10-foot plank is leaning against a wall. If at a certain instant the bottom of the plank is 2 feet from the wall, and is being pushed toward the wall at a rate of 6 inches per second, how fast is the acute angle that the plank makes with the wall decreasing? So that's just reading it out, but you might want to take a minute to read it with your own eyes and try and decide what kind of problem it is and what is the given information and what are we required to find. So what I like to do in these cases is I like to make a sketch, and we put our given and our find information, and we can decide what to do. You decide what kind of problem this is and how to use calculus. So in my sketch here, I have this plank, and it's resting against the wall here, which is its vertical line, and then the floor. So it's talking about the length of the plank being 10 feet. So this length here, I'll label 10. And there is a force that's being applied to the bottom part of the plank such that it's being pushed this way. And we find that because it's being pushed toward the wall at a certain rate. The rate is given to us as 6 inches per second. So we know that the rate, or the d by dt quantity, of the motion of the bottom of the plank is 6 inches per second. But in terms of variables, we don't know what that means because we haven't declared any yet. So I'm going to call the distance between the wall and the bottom part of the plank x, and the distance between the floor and the top part of the plank, I'm going to call that y. So then it's dx by dt, which is given to us as 6 inches per second. But because the units that were given are 10 feet, I think the best thing we can do is convert this quantity to feet per second. So if something is moving 6 inches per second, and there are 12 inches in a foot, then it's moving half a foot a second. So let's do that then. So that's equal to 0.5 feet per second. So at this point, we can determine what we're asked to find. It says, how fast is the acute angle that the plank makes with the wall decreasing? So here's the acute angle that the plank is making with the wall. Let's call that theta. And we are asked to find the rate at which it is decreasing as an angle as we push the plank further and further up the wall and towards the wall. So we're looking for this, and we're looking for this at exactly the point where, well, it says if at a certain instant the bottom of the plank is 2 feet from the wall. So when the bottom of the plank is 2 feet from the wall, so when this distance x is precisely 2 feet from the wall. So when x is equal to 2 feet. I'm going to drop units in all subsequent calculations, and in the little bit of board I have left here, we're just going to set up a formula. So look at that. You have your triangle, you have a y side, you have an x side, and what you're going to want to do is you're going to link the unknown variable to something that you know you're going to be able to sub in. And look, we have information about x. X is going to sub in to be 2, and we're done. And we're going to want d theta by dt. And we even have dx by dt. So there's a lot of x's involved, but not so much y quantities. So I think we should link x and theta. And the best way to do that is to use a trig ratio. So the sine of theta then is equal to opposite over hypotenuse, opposite side being x, and hypotenuse measuring 10 all the time. So that's our formula. And at this point, maybe you figured out this is a related rates problem. And it's a related rates problem because we were asking for us to look at the rate of something happening. So rate is always something changing with respect to time. like distance over time is a rate, it's speed, for example, and this is a distance over time rate, curiously. And then here's the rate at which that angle is getting smaller and smaller and smaller. So at exactly x equals 2, what is d theta by dt? Well, we don't have a d theta by dt. We don't even have a dx by dt, so we can use this information yet. You're going to have to take the derivative of both sides. So if you want to take the derivative, you're going to have to take the derivative with respect to time to get your d by dt quantities so you can sub stuff in and solve. So the left-hand side, or LHS for short, is going to become d by dt of sine theta, which is cosine theta times, by chain rule, d theta by dt. And the right-hand side is going to become, we have x over 10, and usually when we take d by dx, we would just get 1 over 10, but it's d by dt, so it's going to be 1 over 10 times dx by dt. Okay. So at this point, I would recommend equating these two on one line and then solving for the quantity that you're going to end up getting in the end. The d theta by dt is unknown. So if you would do that, that would be great. I'm going to have to do that in my next line, but just give me a second or just skip ahead to erase this. And we can continue on this little side here. All right. So if cos theta times d theta by dt is equal to 1 over 10 times dx by dt, then if you rearrange everything, I'll just do it in one shot, but from that bottom line there, I can tell you that the d theta by dt rate is equal to, you rearrange everything, so I get dx by dt on top, and that's divided by, I have to move the 10 over, and I have to, well, I don't really have to move the 10 over, but I'll put it just underneath, and I have to move the cos theta over. Forgot about the cos theta. It's 10 cos theta. So algebraically, you just do some stuff, and that's what you get. But at this point, we have to think back to what we had, and hopefully you have that written down somewhere or you remember. We know that dx by dt is equal to 0.5. But we don't have theta. In fact, all we have is the instant where x equals 2. That's all we have. So you have to think about the triangle one more time. So here's the triangle one more time, but miniaturized, where this is going to be a 10, and the snapshot we're looking at to find our rate of change is going to give us that x is 2. So I think what we might want to try is finding theta by finding cosine of theta, and then just plugging in whatever ratio that is into here. So I have that the cosine of theta is equal to, remember that this was a y, cosine of theta is equal to y over 10, and x squared plus y squared is equal to this hypotenuse squared, so 10 squared, and that's equal to 100, and x equals 2. So then y squared, moving everything over, is 100 minus 2 squared, so minus 4, which is 96. And I'm just going to have to move this 2 up here because too many things are in the way now. Let's put this triangle away. So here now you have an equation. It's going to give us y, so therefore y is equal to the square root of 96. I'm not worried about the negative root because we're dealing all with distances of this right triangle, and that reflects the physical situation, so no negative roots needed. So y is root 96, and cos theta is y over 10, and cos theta is root 96 over 10. Okay, so we can plug in everything that we know, which I'm going to do all the way down here. So I'm going to get that, therefore, d theta by dt is equal to dx by dt was given to us to be 0.5. Remember? Because it was given in inches per second, but we wanted it in feet per second. And then we're going to divide that by 10 cos theta, which is 10 times root 96 over 10. Ooh, fancy. So the 10s cancel. And so the rate of change that we're looking at is just going to be a 0.5 over the square root of 96. And if you're looking for units, that's going to be in radians per second. So radians per second. I'm just going to get rid of that so you can kind of see what's going on. And I'm going to change that to a 5 that looks like a 5. So at this point, you got the number. You journey from the sketch to a formula, taking the derivative correctly with respect to t and employing the chain rule. And then you did some algebra, realized you were missing something, had to use the instant in time that we're given in order to find it, where x equals 2. But there is something that you might have decided to do that I didn't do here. And because it talks about this angle decreasing, and in fact then dx by dt is going to be a negative rate of change because x is getting smaller as time goes by. So maybe you would have decided from the very beginning that dx by dt is not 0.5, it's negative 0.5. And if you do that, you get a corresponding negative rate of change for your theta with respect to t, which makes sense because that angle is just getting tinier as time goes by.